I'm going to start off with an awkward question. How many people here have seen Ant-Man 2, the movie from Marvel? Okay, not too many? A few, okay. Some don't want to admit it. I get it. Okay, here are a few clips so that the other
Quantum
ones...
in front of everything?
Quantum phase.
Quantum spectrometer and
Quantum anomaly.
quantum research.
Quantum entanglement.
Quantum entanglement between the quantum states of
Quantum technology. Quantum energy.
quantum energy. Quantum system.
Quantum healing particles. Quantum tunnel.
Quantum void.
Quantum.
Okay, so you get the point. The point is quantum is a buzzword, okay? And even in movies, it's a buzzword. And I think one of the things I want to do today is try to demystify that a little bit, okay? And I want to show you how to do it with JavaScript, okay? So that's the challenge here. My name is Miguel, and let's get to it. So the first theoretical, very hard to understand concept is that of a quantum spectrum, which is in fact a made-up thing I have to distinguish different roles of people that are working in quantum computing. So on the first side of the spectrum, we have the physicists. These are the people that study the laws of physics, and they try to understand how the universe works. And then we go to the scientists. These are the guys that like to experiment and try to see if the first ones were right or wrong. Following up, we have engineers, and these are the people that focus on building quantum processors, okay? So real hardware. And this is actually a very hard job because you need very good conditions. You need almost near absolute zero temperature to run, to develop your qubits. And then afterwards, we have the software engineers that try to connect what we also know as hardware to the software. And finally, we have developers. And as we all know, developers work hard, okay? So today, I'm going to focus on these three roles so that you get a little bit of all the parts that are essential for it to make sense. In the top right corner, there's a link with some concepts that were to a gist with some concepts that I'll be using throughout this talk. It might be useful if you want to keep some of them not in your RAM memory, let's say. So why do we focus on these three roles? The first one is so we can demystify. So next time you go and watch a Marvel movie, you're not awed by all the terms they're making up. Then we want to get our hands dirty, and this is not related to coronaviruses at all. And finally, we want to benefit from it. We want to know how this promise of quantum computing can be beneficial for today's companies and for us, for developers. So let's start off with a definition of what quantum computing is. Essentially, it can be considered as leveraging natural things that happen. And these things happen at a very small scale. They happen at an atomic and subatomic scale. So we are all used to our laws of physics. If we take a phone and we drop it, it will fall. When we go into a very small level, and that is at the size of an atom, and even smaller, those laws change. And they change in a way that we can't even understand some of them. And we don't know why they happen. So a lot of the things I'm gonna talk about today, you can ask why at the end, and I will say, I don't know, and no one knows, okay? But we can see its effects, and we can see that it actually happens, and there's enough substantial proof to believe it is true. And well, the end goal is to produce computations, right? Okay, so I assume everyone knows what a bit is. Yes, okay. Now, let me introduce you to the concept of quantum bit, or in other words, our word, qubit, okay? So I'm going to use an example. But the main message here is that a qubit can be implemented in many ways. This is an easy way to understand how we can actually imagine it. So take a hydrogen atom with only one electron orbiting around it. And the thing about this electron is that it as some of you may have studied, it has a particular level of energy. So it jumps from orbit to orbit, and these orbit jumps are done in a quantized way. So they're discrete jumps. The electron is not between 0 and 1. It is either in 0 or in 1. But there's a twist. And the twist is called superposition, okay? Superposition, as I'm sure some of you have heard already, is essentially a state in which there is neither just a 0 nor just a 1. It's a combination of both, and this combination is not something that we're used to. And so to kind of understand this better, there's this famous thought experiment called the Schrodinger's cat, which I'm sure you've all heard of. But the main message here is that, okay, I'm actually gonna go through it. let's say we have a box, we put a cat in there. If you don't want to hurt cats, you can do it otherwise. And you put inside a trigger with a 50-50% chance of letting out some poison, and it will either kill the cat or not kill the cat. So while the box is closed and that moment has passed and it may have or may not have triggered, you don't know if the cat is dead or alive, okay? So if we are considering this state as we do in quantum physics, we consider it in a superposition of both states of dead and alive. The cat is not half dead and it is not half alive. It is both at the same time. And then the curious thing, and this is the point where we see that we cannot see some of these phenomena happening, is although we see manifestations of this, because if we take 100 boxes with 100 cats, I'm not giving ideas to anyone, and if you do that, 50% of them on average will be dead and 50 will be alive. But you don't know that until you open the box. And once you open the box, you cannot go back. You cannot go back and have a half dead, actually a dead and alive cat at the same time, okay? So the idea is really, we know that it happens and we can see its manifestation, but it's not straightforward to observe. Actually, so far it's impossible. Okay, so something you're more used to, a circuit. This is a logic circuit, and it will make sense today to see the way we write quantum algorithms is also a circuit. And this is called the circuit model. It's not the only way to approach this topic, but it's one of the main ways, and hopefully it's not too strange for most of you. So some of the components that you'll see are a horizontal line, which is a qubit. 2 lines go for a classical bit, and if you see the measurement there, the measurement is like opening the box. We have something that used to be a qubit and now is a bit, because we can either have an alive cat or a dead cat once we open the box. And also gate there is just an abstraction to operations that we execute on our qubits. So like a normal bit, you can, for instance, do a NOT, which is just turning your, let's go back to electron example, putting it in the other orbit, and then go back again. And then there's the Hadamard gate, which is a very special gate because it is precisely the gate that puts a qubit in superposition. So it stops being in 0 and it starts being in a combination of 0 and 1. Okay, so now we've digested a little bit on the physics part. Let's get to some tools where we can actually try this. I've left a few on the right for reference. They are in the gist, so you can look them up later. And in this presentation, I'm going to go through 3 of them. The first 2 rather quickly, and then with some more focus on the last one. So Quark is actually just a web interface, and it's a drag-and-drop web interface where you can test some of this knowledge. I have a GIF here of it working, and I'm going to use it to explain the main components in this circuit, just so you get a notion of how it is all composed. Do not try to understand the logic there, just try to focus on the shape, okay? So each horizontal line is a qubit, and as we saw before, our qubits, unlike traditional logic circuits, they do not merge. They exist throughout the whole computation. And they all, typically by default, they start at state 0. And when we have a lot of them, we consider it a circuit. And then we can apply gates. In this case, the Hadamard gate. It means we're putting our qubits in superposition. And if you look to the right on this second qubit, we see it's a 50% written there. That means it's typically on a superposition of 50 to 50%. And then we also have gates that allow us to make these qubits interact with each other. So we don't combine them, but we make them work together. And we're going to see how we can do that later. Okay, and then we have measurement. As we've seen, we're trying to get something that used to be a quantum state into a real state. By the way, I'm not going to have enough time to explain this, but the block sphere is actually a very interesting visualization of a qubit state. So, for instance, when you have a 0 state, you have a state in the axis, and you can just, as you apply functions to a qubit, it will project differently onto the block sphere. So, if you want to explore these more theoretical concepts, you have this reference for later. So, Qiskit. Qiskit is, I brought it here because it's as more of a framework than actually something where you can get a as I won't be using it to get our hands dirty, but I'm using it as a reference because it's a very good organization of the whole process of doing quantum computing, okay? So you have the low-level stuff that is building the hardware and interacting directly with it, which is Terra. All of these names, by the way, are acronyms. I don't know all of them, but I'm going to show you one at the end. And then you have software engineers, which also work at that level, so they can build the circuits and implement some algorithms from papers and so on. Then you have those scientists that like to do experiments. There's also a market for those. Those two parts of the framework, Air and Ignis, are mainly focused on simulation and simulating noise parameters, because one thing that you should also be aware is that implementing a qubit is not that hard. Implementing 2 is a bit harder, but when you have 8, 10, it starts getting very hard because they interact, there's noise. You need to have a very, very stable system. And so there's also some work being done on how to be able to perform computation even if your system isn't perfect. And then on top of that, we have Aqua. And Aqua, as we're going to see a little bit later too, is very good for this high-level approach, and it's an abstraction layer. So when you're writing code for the Aqua interface, you are almost unaware that you're writing quantum computing code underneath, because you call your code as you used to. Let's say you have a support vector machine algorithm. There's already an implementation for that, and it will automatically use your data and map it onto a circuit, which you can then run. This is maintained by IBM, of course. All right, so Quantum Peep. Quantum Peep is actually not maintained by a company, so there's a benefit to that, which is it's not biased towards any cloud provider. To install it, you can just do npm install Quantum Peep, and there's one other library, CircuitViz, which I use in this presentation, but it's not mandatory. So let's see how we can make a Hello World circuit. So the first step is to create a program, and program here is our circuit. Let's say they're synonyms. And then we just invoke the add method, and we go and add an X gate on our qubit 0. And when you see the numbers there, those are numbers that you can choose. You just need to be coherent, and they will be mapped onto the text after the underscore down here. So we add an X gate, as we see on our first qubit, on qubit 0. And then we measure it. And as you see, we're measuring from a qubit onto a bit. And we do another measurement for the second qubit. And then we visualize, and this is essentially how you can create your first quantum circuit. Good thing, as I was saying about Quantum Peep, is that it runs on two different providers. And at the moment, these are the only providers that give you access to free stuff. They also have paid versions, which are more powerful, of course. But at the moment, IBM Q and Righetti Computing are the main ones providing this for people to get their hands dirty. So how can you use Quantum Peep to connect to those? You just do this. On the left-hand side, I actually used a Docker image for a simulator that is supposed to simulate their actual processor, but you can get your credentials from their website. The same goes for IBM processor. You can just log in. I actually included the link in the gist. You can just create an account on IBM Q Experience, and they'll get you a username token. And you can actually take the previous example, do this, and afterwards just run it on a real device. The thing is, these devices are, I think the biggest one is 16 qubits, which when I say this, you're probably thinking, okay, 16 qubits, that's not a lot because I cannot do a lot with 16 bits. The thing here is a qubit is much more powerful than a bit, okay? And with 16 qubits, you cannot do things that are more powerful than what you can do today with good computers. But as we'll see, there's an enormous potential in just having 8, 12 qubits, okay? And remember when I told you about having 1,000 boxes with cats? So the thing about this is if you only have one box and you open it, you cannot infer anything about what the distribution between the states was. So you actually need to execute your circuits many times. And when you execute them many times, you get a good approach of, let's call it the probability that your poison would be released. And afterwards, you can just use that result. That result is usually just a bit version of the final state. You can also use Quantum Peep to query the devices available. Sometimes they go down for maintenance. Sometimes they also have some simulators. which are a little bit more powerful at times. Okay, so how can we, this is very similar to our Hello World problem. How can we measure and visualize a quantum circuit, okay? So the first, on qubit 0, we're just doing a NOT, okay? So this is pretty straightforward, classical computing. And then we're doing 2 NOTs on the second qubit. So what we're expecting is to see 1 on the first qubit and 0 on the second. And when we call our provider and we get a result, which we can then plot as a histogram, in this case we have 1.000 hits for 10. So you actually have to read it from right to left or top to bottom. 1 is qubit 0 and the 0 is qubit 1, okay? So this is pretty straightforward, okay? Now, what happens when we get into the superposition measurement is what we talked before. We need to put our qubits in a superposition, and then we'll measure them and get something we can actually look and understand out of. All right, so let's do a simple circuit. Just that special gate, the Hadamard gate, we're only applying it to qubit 0, and we're leaving qubit 1 to be just 0. So what happens when we execute and plot this? We get something very different now. We get a distribution between the results. As you see, it's not actually 50-50 because there's some noise, and if you actually want greater accuracy, you can call it more times, but typically 100 to 1,000 is a good number to execute your circuits. And as you can see, on approximately half, we have 0, 0, meaning that when we open the box, the cat, let's say, was dead. And on the other side, we have 1, 0. So when we open the box, the cat was alive. Now, there's one strange phenomenon that happens, and Einstein referred to this as spooky action at a distance, which is quantum entanglement. And entanglement can be seen as, let's say I have 2 qubits, okay? I can hold them in my hands. I bring them very close together, and I leave them to interact for a little bit. And then I happen to have one of them in a superposition. And when I bring them very far away, when I collapse or when I measure one of them, the state of the other will also collapse. So they become entangled. And this can be seen as a correlation. Why does it happen? I don't know. No one knows, okay? But the interesting thing is that it does, and there's a lot of fun things we can do with it. I'm introducing now the CX gate. C is for controlled. X, as we've seen before, is for not. And what this gate does is it will flip the second bit if the first one is a 1, okay? So if we had a typical circuit, a classical circuit, we just need to execute it once, and we would get a result that would be deterministically based on our first qubit. But if we do what we're doing here, which is put the first qubit on a superposition, what do you expect to happen? The result will be something like this, where we have 0, 0, and 1, 1. As you see, the result of the second qubit is dependent on the first one. So it will not happen, we don't have 0, 1 or 1, 0, we only have 0, 0 and 1, 1. If you want to learn a little bit more about this later, this is called a Bell state, and it's like one of the first ways to understand what entanglement is. Okay, so let's try to use this for something useful. How would you, okay, typical random numbers, and that's why I'm writing through with a different color there. Typical random numbers, as most of us know, are based on a seed, and that seed enters a mathematical function that will generate pseudo-generated random numbers. So the first application that we can actually use quantum computing for is to generate numbers that are truly random. So if we have a perfect qubit, or a qubit that is very good implemented, we can just put it in a superposition and measure it, and we'll get a 0 or a 1 randomly. How could we write a function, for instance, to generate a random number with n or len number of bits? I wrote it like this, so created a new circuit. I know I could have used only one loop for loop, but I decided to do it like this so it gets prettier at the end. And we add the Hadamard gates, and then we measure for each qubit, and then we just return it by reading the result and returning to the person, to the user. How would you look if you call this function for a length for random number? Like this. So you have the 4 Hadamard gates, the 4 measurements, pretty straightforward. This is how you can get truly random numbers. Fun fact, there are like companies that do this as a service, okay? Which is kind of strange because nowadays everyone can do this, but it still happens. All right, so now let's try to understand why having 16 qubits can actually be important, or compared to 16 bits can actually be much more powerful. So the trick here is parallelism. Let's say we have 1 qubit and we put it in a superposition. Then we have 2 possible states. And if we run a set of instructions, a set of gates, an algorithm on that 1 qubit, we will have tested 2 states at once. What happens if we have 2 qubits? We will do it in 4. If we have 3, 8, and so on. So you see that this is an exponential growth in the power that you can compute with only a few qubits. Is anyone familiar with this problem? I would give you a very large number. You try to separate it into primes. Yeah, this is. There's actually going to be another talk at QCon focused on security and quantum. And I'm just introducing it here because I think it makes a lot of sense to understand why quantum computing is interesting. Let's say this problem is the base of current encryption methods, namely RSA. So when you see encrypted communication over HTTP, so HTTPS, it's based on the fact that this problem is very hard to solve. Meet Peter Shor. This gentleman here created a theoretical quantum algorithm to solve that problem using a linear, or better said, a polynomial time. So when we actually compare what we can do with classical computers towards that problem, so essentially trying to break an encryption, it's an exponentially hard problem. And that means that if you have a very, very long number, you're not going to have enough computing power on Earth to do it. What he did was create an algorithm that can do it linearly. So you only need to have 1 or 2 more qubits to quadruplicate the amount of numbers you can actually compute. So this was the first time this algorithm was put to test was on a very, this was back in the days, a very old quantum computer where they figured that 15 equals 3 times 5, which is an achievement at the time at least. Recently, another company, Zapata, has brought this number up to that, which is not a lot. And so, as you can see, there's still, as we're going to see throughout the rest of the presentation, the thing about quantum computing is that we have a lot of resources already. We have a lot of algorithms. We have a lot of tools that we can use. What we need is good implementation of qubits. So the challenge is actually in building quantum processors that are good enough, that are very stable, that don't have a lot of errors, so that we can still beat classical computing. So let's try to move on to another layer of abstraction. How can we use this on a higher level? So I'm going to introduce 3 techniques. I'm not going to explain them very thoroughly because, well, it would take a lot of time and headaches. But first one is quantum approximate optimization algorithm, QAOA. And what this is a theoretical algorithm that can be used to find solutions for CSP, so constraint satisfaction problems. What this means is if you have one of those problems or any other problem that you can map into a 3-set or a constraint satisfaction, you can use this algorithm to have very good results in a very small amount of time. And if you're wondering if there actually is a quantum tunnel, well, there is. There's actually a technique called quantum tunneling, which you can use to find solutions to problems. Essentially, this is used for optimization problems, and it's based on some interesting things that happen at a very small level, where you have particles that can jump through energy states without rising their energy level. And that's called the tunnel effect, and in fact, there's something called quantum tunneling. So they didn't make that one up, but there are no quantum healing particles, as far as I know. Okay, one other very interesting method for solving optimization problems using quantum computing is from a high perspective, what you do here in adiabatic computing is you have a problem, and you can describe it as a combination of a quantum state, so several qubits interacting with each other. And what you do is you just put that system to rest, and it will start getting increasingly lower levels of energy. And when it reaches the lowest level of energy, you get your solution. So these are three very interesting things that are already being used, and some libraries can already implement them. But there's one thing, and this is the thing that's preventing quantum computing from exploding already. So anyone here knows what quantum supremacy is or heard about it in the news? Okay, a few. So those ones are not going to be impressed by my composition of quantum of solace and Born supremacy. Essentially, quantum supremacy is a moment in time, okay? It's a moment in time when the classical computers that simulate quantum computers, okay, because we have simulators for quantum computers, can no longer simulate the quantum computers that we have. So, as a matter of fact, there's this company called Google that claims they have achieved it. This was in September last year, and there was a lot of fuss about it. Some people came forward and said, oh, but this is not really that hard if you do this to the problem. So it's still an ongoing subject. But the lesson is, although we're not very far from it, and we've seen like companies like Google, IBM, Microsoft, and so on, they're saying that they have quantum computers with 50, 60 qubits. But the thing is, even after we reach it, we still need to build even better quantum computers so we can have actionable computing that compares to what we have today. So the ideal goal here is to have a problem that's very hard to solve today, that your companies probably cannot solve optimally, and will eventually, and I don't want to say how long because I don't know, it's one of the things I won't know, but we're walking towards it, and that's the promise of quantum computing. It's the fact that you can easily solve problems with it that you couldn't otherwise, and that you cannot with classical computing. Okay, so as a matter of fact, there are a few efforts, for instance, from Azure, from AWS, and from Righetti, which is that company that I mentioned previously, to already have companies use quantum in their products. What's the thing about it is, well, this is not as straightforward as you use your SDKs or APIs, or you just go to AWS, create an instance, start using. It's actually on a case-by-case basis, so they just talk to you, see how your business problem can actually be solved using a quantum approach, probably with one of those three algorithms that I showed previously. And then they'll just let you have some points on how to do it, how to implement it, and eventually in the future take advantage of it. So the thing is, they're selling it already, although people cannot still take that much advantage out of it. And that's the message I also want you to get today. So just introducing a little bit further QuizKit Aqua. And now I can say that Aqua stands for Algorithms for Quantum Computing Applications. So as I said, these are acronyms. It's organized in a very neat way. And the bottom part is going back to QuizKit, where you have your typical roles of scientists and physicists that work at a very low level. And then you have the engineers that write the circuits and implement the algorithms that maybe those two develop. And then on top, and this is the interesting thing, and the thing you can actually do today, is you can implement algorithms as a developer without knowing that you're writing quantum computing code underneath. And that's very interesting because if you can do this today, the only thing is to wait for that moment when quantum computers do overcome classical computing. And so these are really good efforts from my point of view, helping people understand how they can actually benefit from quantum in the near future. So a few takeaways for quantum developers. The things you can do today are use JavaScript and actually other languages to learn how to write circuits and how to run them on real quantum computers, although those are not very powerful yet. You can invoke them for free, and creating an account is actually quite straightforward. You can do it in a few minutes. And also, there are a lot of things that you can get out of the box already, especially on QuizKit and actually on other libraries and frameworks, where you can just have your problem, even if it's a small one, and actually write code, and you'll see it. It's actually an interesting experience to know that you're writing code that's not running on your processor, but actually on a quantum computer. Nowadays, for instance, for IBM's cloud processors, you usually get like 100 people ahead of you in the queue, so you have to wait a little bit. Ideally, in the future, it will be faster than that. I remember the days when it used to be like this, but I'm not going to cry over that now. So for tomorrow, these are also things that I want you to leave this place with. Beware of traditional encryption, and I would advise the other talk. I think it's on the final day of QCon. And one interesting thing is also focus on those algorithms that run quantumly, but can actually be mapped onto things that we understand. Probably everyone here has at some point have to dealt with constraint satisfaction or optimization or minimizing something. And so if you can identify problems that you have as constraint satisfaction or as an optimization problem, you're one step away from being able to benefit from quantum when it arrives. And so for the moment, we must wait for quantum supremacy for this to have a real impact on our businesses. But we can take a few steps ahead of the competition and try to understand it at the moment and get a better notion of how we can benefit and how we can use it. So to summarize what I talked about, hopefully we've demystified some of the things about quantum computing. We've got our hands a little bit dirty. Again, no coronavirus joke. And we know how we can benefit from it. The thing here to notice is we cannot benefit from it a lot today. And it's an important thing to be aware, because when you see these companies like Azure and AWS and so on advertising their quantum cloud services, they're promising something that they cannot deliver yet. So we must be aware of that. Okay, so time for questions. Thank you for your time.
Thank you very much, Miguel. That's fascinating stuff. I'm going to start with two questions. So the first one is, are you aware of any non-FANG companies, so not the big companies like Google or Azure, that is using this technology for real business problems today? Okay. So that's the first question. And the second one is, as a developer, we always have this choice where we're trying to stay ahead of the game and make sure that we are able to earn a living in 5 years' time, in 10 years' time, which means we have to choose what we learn carefully. If you choose to learn Kubernetes, that's a lot of learning to do. Machine learning, there's a lot of stuff to learn there. Even serverless, you saw in the last talk, there's quite a lot of stuff to learn. And you have to make decisions all the time about what you're going to learn. How much effort is it to learn this basic stuff compared to, say, Kubernetes or something like that?
Okay.
And it's not just the coding, obviously, there's a bit of maths involved as well.
All right, so answering the first question, I know of a few major companies that are using quantum computing, or claim to be. For instance, Volkswagen has been working with a company called D-Wave, and D-Wave usually claims they have 2,000 qubit systems, but the thing is they use a different type of approach, and the fact that they have 2,000 qubits doesn't really mean that they can process as much as, let's call it, good quantum computers can. So they actually focus on adiabatic evolution, the last technique that I showed you. And although they claim to be working with Volkswagen to optimize some processes, they don't do it in a very transparent way. There are a few other companies like KissywWare that tried, and Righetti as well, they're mostly focused on identifying problems that can be solved with quantum and writing code to do it. But the thing is, although some companies do claim they are taking advantage of it, you should take it with a grain of salt. Okay, that's the first question. As for the second, it really depends on how deep you want to go. For instance, what I brought here today is kind of a high-level perspective. And if you're a software developer at a company that might be using quantum in a few years, I think something like this would be enough. Or if you want to try it out and just see how you can actually run something on a real device, that's actually very fun. if you really want to study this and if you want to learn more about what kind of algorithms exist, because there are algorithms for a lot of things, for searching, for sorting, and so on, that takes a lot more time. So it really depends on how committed you want to be. But I'm an advocate for exploring things, and exploring quantum computing is something that I've dedicated a lot of time to doing. But I also know that I need to keep my feet down on earth and explore things that are useful on my day-to-day work. So I think that answers both questions.
Absolutely,
Yeah.
thank you. Would you like to ask any questions?
This is from the skeptic perspective of
Thank you.
maybe a skeptic about quantum in general, because it's a way to disguise our own capacity just to be all-knowing, instead of just moving in a deterministic way where you know that in a circuit, if the input is going to go one way, it's going to always come out, in a deterministic way. You're just disguising that inside a gate that has a random state inside, but that's because you don't know it. But it's not really quantum, it's just like you don't know anything. So just basically, it's like it's a metaphor of the Schrodinger's cat. Quantum is a bit like even these computers that you can access, there's no real way to know if they're actually doing it at a quantum level. It's just that they're disguising that randomness in a way that is harder for us just to...
Okay, I get your question.
Yeah.
So just to clarify, so you want to know how can we know that they're actually running on quantum, they're doing true quantum implementations? That's the question, essentially.
Yeah, basically, and also if that...
Yeah, okay. Okay, so for personally, I've seen a quantum computer in person. I handle the plates where they actually implement the qubits. I believe it, okay? And I think these claims are not coming out of nowhere. The theory has been developed in the past 100 years. And they actually implement things there and run algorithms that would take a lot of time to simulate. And if you wait a few more years, when we reach the quantum supremacy point, it's going to be undeniable that it works. So to answer your question, I can answer your question in 5 years, 10 years, okay?
But if you allow me to say,
Yeah, no, of course.
it's wrong, but that's like a bit the response that you will get from a call. Just trust us, and things will get better, or the doom will come, or something will happen in 10 years, but at the moment, there's nothing tangible for it. It's like, you will have an open the box to be that we are doing real quantum, to be that we are not. You know what I mean?
Well, they say every sufficiently advanced technology seems like magic. So do we have any other questions? Yes.
How do we have to reach quantum supremacy before traditional encryption methods become a problem? And is there anything that we can do about that now? Can we use better encryption methods? Do anything about that?
Okay, yeah, that's actually a very interesting question. This is a thought experiment. Let's say you are using your web browser to communicate your encrypted stuff, and I'm capturing those packets, and I save them, and let's say in 10, 20 years, I go and I decide to use these algorithms to crack it. That's possibly a problem, okay? That's possibly a problem that's being addressed, and there are actually a lot of research efforts focused on doing quantum encryption, so being able to transit from what we typically use in a classical computer to a quantum one. And I would actually advise the talk that I mentioned on the last day, because it's totally going to be focused on quantum encryption and security. And I'm sure you'll get some more in-depth answers on that.
If I may impose with another question, which leads on from the question of when does quantum encryption break classical encryption? Is it possible, do classical algorithms exist that cannot theoretically be broken by quantum algorithms?
Okay. When you say broken, you mean you were talking in terms
it's a
of
mathematical
encryption?
question.
Yeah, okay.
Is it possible that such things exist?
No,
or is it fundamentally impossible? Does quantum break every classical encryption?
Okay, I cannot claim that because I'm not an encryption expert, okay? But the feeling I have is it's mostly a matter of time between when you publish a new encryption algorithm and you can find a quantum approach to do it. So sometimes encryption is focused on mathematical problems being hard to solve, just like this one. And if you can find a way to solve those problems quantumly that is actually easy, when I say easy, I say polynomial, then it's just a matter of finding the right algorithm for the right problem.
So we lose every time.
I don't want to be a fatalist, but...
Do we have any further questions before we wrap up? Okay, thank you very much. Thank you very much.
Thank you.